Okay, this is mirrors part B. One of the things I want to do before we really get into the math of doing mirrors is I want to go back to the very first page where we were talking about this part here, where we're looking at information, new information. We're looking at C and we're looking at focal point within the mirror. One of the things that I want to clarify for you, and I didn't really realize the importance until I started doing some questions and the language changed. But this part here, the center of curvature, the definition is the center of the circle if the mirror was a complete circle. Well, if we're looking at the center of a circle right here, if we go out to the edge of the circle, this is what we know to be radius. And so in this particular case, C, which we're used to seeing a letter represent the word circumference, is not actually the circumference. And I know I wrote that here, and that was incorrect. It's a lazy man's way of writing it, but this is center of curvature. And so when you get into the questions, they don't tell you the center of curvature this or the center of curvature that. They give you the radius. And I need you to understand that this C, meaning center of curvature, is the same value as R. So we could write R is equal to 2F, or F is equal to R divided by 2. Because what's the other piece of information that they could give you is they could give you the circumference of the entire mirror if it was a circle. So you could be looking head on a mirror, and then like if you're looking at a mirror like this, they could say that the circumference of the mirror is this. And so it doesn't matter if we're looking at it 2D this way or 3D coming out this way, it's still going, R is still going to be the same, because if we turn that mirror into a globe, going from the center here to here should be the center of going from here out this way. Okay, so just understand that C in this particular case is not the word circumference, that it's a misnomer. It's actually radius. Okay, having explained all of that to you, we are going to get into the math of a mirror. And what we see is nothing has changed. It's still 1 over the focal length is equal to 1 over the distance of the image from the mirror to 1 over the distance of the object from the mirror. And magnification is equal to the height of the image divided by the height of the object, which is also equal to the negative of the distance of the image over the distance of the object. So that hasn't changed. None of this wording in here has changed. The formula is the same. What does change in here slightly is the definitions, and only in this one spot. Only this area here where we're talking about focal length. This is the only component here that's different. I encourage you to flip forwards and backwards between your notes. So let's look at the distance of the object. Again, we are the ones that are creating the image, so the distance of the object is always positive. Okay, and we never put the object behind the mirror. It's always in front of the mirror. If it's a real image, it will be positive. It'll be on the same side as the object from the mirror. And this only makes sense because if you are looking in a mirror, you are looking at your reflection, and your reflection has to be in front of the mirror. If you have no image, we call that a virtual image, in that your image is behind the mirror, it would have a negative value. Your DI would have a negative value. this would be known as behind the mirror. And there would be no reflection. So it's not that you're a witch or a vampire or any of those stories. It's that it's a virtual image. Okay? All right. If we're looking at the focal length, we know from our notes, our previous notes, that, I just want to bring it up. Okay. From our previous notes, it's positive for a converging lens. And what happens here is the language is going to change. We're going to go from converging and diverging lenses to concave and convex lenses. That's what changes, is the language. For a real image, it's positive, and that is for all concave mirrors. All concave mirrors. And that's when the object is placed farther away than the focal point. Okay? Now, a virtual image, your focal length would have a negative value. And it's for all convex mirrors. So if your question mentions the words convex mirrors and gives you a focal length, you know you need to make it a negative. So all convex mirrors, and when the object is placed between focal length and mirror on concave mirrors. Okay, so if it's a concave mirror and the object is placed farther away than the focal length, it'll be a real image. If it's a concave mirror but the object is between the focal length and the mirror, it'll be a negative value for your focal length. Or else it's a virtual image, and that will be that it's because it's a convex mirror. Again, when we draw it, the height of the image is upright if it's positive. It's always upright for an object, and an upright image on magnification will have a positive value. So you can have a larger value for magnification. You can go from 1 to 2, but it depends on the sign if it's going to be positive, if it's going to be upright or inverted. If the height of the image is negative, it's inverted. So that means that your line is like this. If it's never negative for the object, because we always write it in a positive format, and it's inverted if the magnification is negative. So again, an image like this. Okay, so virtual, if this was your mirror and this was your object, it would be back here, distance of your image. It's a virtual image if it's behind the mirror in a convex mirror. Or if the object, or it could be like this, and here's your object, and here's your focal length. Those will give you negative values, and it will mean that your image is behind the mirror. Okay, this chart is really important for you to understand, because you really need to understand what the positives and the negatives mean. If the question is just telling you the focal length of a convex mirror is this, then you need to know that when you do the math, you have to be the one to put in the negative. Okay? So you have to understand this chart. You have to understand the picture that you're looking at. Let's look at the first question. An object is 2 meters tall and is located 7 centimeters in front of a convex mirror that has a focal length of 3 centimeters. Well, what does that, let's just draw that out. I know we're doing math right now, but let's just draw that out. So here's our principal axis like this, and we're 7 centimeters from a convex mirror. And the focal length is 3 meters. Okay, so a convex mirror is a mirror that's bulging towards the object. Here's the object. This is our focal point. Okay, our C is always 2 of the F. So if we wanted to draw that in, we would put C here, the center of the curvature. Okay. And so what we're looking at when we do this, and it's 2 this high. Okay, so we can go parallel to the mirror. Of course, I didn't make my mirror big enough. And you wouldn't do this on a math question, but I just want to show you how we can prove that those things happen. And then, oops, convex mirror, the focal length is here. Pay attention to the language, isn't that what I tell you? Okay, so we went to here, and we're going to come through the focal point, this. Then we're going to come through here to the focal point. And we're going to go parallel to the principal axis. And then we're going to go through the center of the curvature. And this is where our image is. Okay? So when we know it's a convex mirror, we know that this is going to be virtual. Well, yeah, it's going to be virtual. It's going to be behind the mirror. Okay? We know from our picture that it should be upright and it should be smaller. So we can do it this way. We can absolutely draw it out, and that would be good, but it's time consuming. We can also figure it out mathematically. So our object is 2 meters tall. It's located 7 meters in front of a convex mirror. So distance of the object is a convex mirror. And the focal length is 3.0 meters. Now let's look at this. This is a convex mirror. A convex mirror, the focal length is always negative. We have to add the negative. Okay, we need to understand that piece. The distance of the object is always positive. The height of the object is always positive. Everything else can vary except for these pieces. So it says, what is the size of the image produced? So it's looking for the height of the image, right? We can figure this out. Height of the image can be found from this formula. Hi over HO is equal to negative DI over DO. We have this piece of information and we have this piece of information. However, we don't have this piece of information because this is what we're looking for. We find this from 1 over F is equal to 1 over DI plus 1 over DO. You can have DO plus DI, you can have DI plus DO. It's an additive property. 1 plus 3 or 3 plus 1, they both give you 4. All right. Now we need to find DI, so we're going to go 1 over F minus 1 over DO is going to be equal to 1 over the distance of the image. And so for that, we see 1 over negative 3.0 minus 1 over 7.0, and we're going to get negative 0.47619 inverse meters. So meters are still in the denominator at this point. This is 1 over DI. That's what this answer is. We need DI. In order to find that, we need to go 1 divided by negative 0.47619, and we get negative 2.1 meters. So because our distance of our image is a negative value, we know that it's going to be virtual. Okay, it's behind the mirror. Once I have our DI, we can solve for HI. HI is going to be equal to negative DIHO over DO. So the distance of the image times the height of the image divided by the distance of the object. We know we have negative times negative 2.1 times 2.0 divided by 7.0, and we will get a value of positive 0.60 meters because a negative times a negative is a positive. So again, this is us paying attention to our signs. That one we had to add. This one we need to make sure we include in our formula. Okay. Now, the height of the object, this is the answer, 0.60 meters. And then it asks us, what are the characteristics of the image produced? From the information provided, we have a positive value here. And when we go back to our notes, a positive HI means that it's upright. It doesn't matter if it's concave or convex. A positive value for our HI means that it's upright. So this is upright. So we have upright, virtual. And then when we look back here, the object is 2.0 meters tall. And we look back here and we see that the height is 0.06 meters tall. So we can also say that it's smaller. Now we know that that's true because we went and did all the hard work and drew the picture. It's upright, it's virtual, and it's smaller. So this drawing here proves, or the math proves the drawing. They both confirm each other. Let's look at question number 2. An object is 3 centimeters tall, is placed 10 centimeters in front of a mirror. What type of mirror is being used if the inverted image is 1.29 centimeters tall? We're not going to draw a picture. We're going to trust our guts to give us the right information. So let's just start. This object, this is HO. Height of the object is 3.00 centimeters tall. Is placed 10 centimeters in front of a mirror. DO is 10.0 centimeters. What type of mirror is being used if the inverted image is 1.29 centimeters tall? So height of the image is 1.29 centimeters. And when we go back to our chart, the height of the image, if we want it to be inverted, we need to give it a negative sign. So this is where this summary chart's really important. So we're going to give this value a negative sign to indicate that it is an inverted image. Okay, at this point, we still don't know what kind of mirror we have. And so we are looking for HI over HO is equal to negative DI over DO. We are solving for, in this particular problem, DI. I'm going to leave DI there. I'm going to move DO. And when I move DO, I'm going to take this negative sign with it. So negative DO times HI divided by HO. And so, excuse me, DI then is going to be equal to negative 10.0 centimeters. And I left the negative out because these two values here are positive values. They belong with a positive value, but the formula carries a negative. So I'm going to leave it as a negative. And then our height image is negative 1.29. Again, the negative indicating that it's inverted. And the height of the object is 3.0 centimeters. When we do the image, we get distance is equal to 4.3 meters. And it's positive. So let's go back to our chart. And what do we see if our DI is positive? It's a real image. Okay, so this here indicates a real image. A real image then will only occur with a concave mirror. Real image, all concave mirrors. It cannot be a convex mirror. It has to be a real mirror. Has to be a concave mirror. So this only occurs with excuse me, a concave mirror. Okay. So stop here. Excuse me, go through and try these practice problems, or not the practice problems. I want you to try this page 228, number 8. Once you do that, then I want you to go through the practice problems. I'm going to go through and do the practice problems, especially because number 5 is an excellence, and I want you to be able to understand the math behind it. All right, so stop it, pause it here, but this is the part that you need to do right now. Okay, I'm going to go through these practice problems. I don't want you to just sit and watch the video and do the answers as I go along. I actually want you to try them and then use the video as a guide to double check if you're not getting the right answer. Some of these get very tricky because you need to remember the sign convention. So question number 1 is asking us to identify the characteristics of an image. And so just using the information that's there, the height of the object is 6.5 centimeters. It's 15 centimeters from a concave mirror. Okay, and a concave mirror tells us a bunch of things. The concave mirror tells us that the F should be positive. All concave mirrors, a real image will be positive. We're going to start out that way. And it gives us a radius. And I want you to remember that radius is synonymous with the C that we've just added to our vocabulary. So the radius is 20 centimeters. And C is equal to 2F. So F would be equal to 20.0 divided by 2, which would be equal to 10.0 centimeters. Okay? We can confirm that the object is outside of the 10 centimeters, right? All concave mirrors, when object is placed farther away than the focal point, the object is 15 centimeters and our focal length is 10 centimeters, so this is going to be a positive value. What are some of the things that we're missing? Well, we need to know the distance of the image because it will tell us the distance of the image. If we get a positive or a negative, will tell us real or a virtual image. The height of the image, a positive or a negative, will tell us inverted or upright. And magnification will also tell us upright or inverted, but magnification will tell us bigger or smaller. Okay, let's start with what we have the most information for. So 1 over F is equal to 1 over di plus 1 over do. I'm gonna leave it on this side because it's positive. 1 over di is equal to 1 over F minus 1 over do. So 1 over 10 centimeters minus 1 over 15 centimeters is going to give us 1 over di. That value is 0.03 repeating. But remember that this is in the denominator, it's a centimeters to the negative 1. So to get di, we're going to go 1 divided by 0.03 centimeters to get a value of 30 centimeters. Our answer is a positive value. So we're going to keep that there. So now we can tell on di, and di, we can say if it's a real or a virtual image. And we're going to look at magnification because magnification will tell us upright or inverted, and it will also tell us bigger or smaller. So M can be equal to negative di over do. We are going to look at negative times 30 divided by 15. M is equal to negative 2. So this piece of information tells us something, and the number 2 tells us something. Positive DI. Positive DI tells us that it's real. Negative M tells us that it's inverted. And number 2, which is a whole number, tells us that it's larger. So this image for question number 1 is a real image, meaning that we can see the reflection. It's inverted and it's larger. So we're going to see an upside down, bigger version of ourselves. Yay, just what I always wanted. A larger version of myself. Okay, number 2. An object is placed 20 centimeters from a spherical concave mirror that has a focal length of 60 centimeters. What is the distance between the object and the virtual image? So 20 centimeters from the concave mirror means that it's 20 centimeters, or DO, has a focal length of 60 centimeters. And what is the distance between DI and DO? Okay, so that means that we're going to add DI and DO. DI should be on one side of the mirror, DO should be on the other side of the mirror. So, what do we know about these pieces of information? Well, when we look here, we see that when an object is placed between the focal length and the mirror on a concave mirror, the F value is going to be negative. Okay? And we know that the object is between the focal length and the mirror because this is only 20 centimeters out to the object and this is 60 centimeters out to the object. So we need to add a negative to this value. DI tells us all kinds of information, positive or negative. And we need it in order to figure it out because there's DI right there. So 1 over F is equal to 1 over DI plus 1 over DO. So 1 over DI then would be equal to negative 0.167 centimeters to the negative 1, which means that DI is equal to 1 over negative 0.167, which gives us a value of negative 15 centimeters. Okay. This negative here, I use pen. This value here, all it tells us is that our image is virtual. In other words, we're not going to see it. It's behind the mirror, which is kind of what we're looking for because the question asked us, what is the distance between the object and the virtual image? Well, we did something right because we got a virtual image. So the distance is going to be, and this is kind of a bad symbol because it's not a change in distance. I know what I could do. Change it from that to this, a total distance. So we got 20 centimeters on one side of the mirror, and we have 15 centimeters on the other side of the mirror. We do not keep this negative. All that negative is telling us, is it real? Is it virtual? Is it inverted? Is it upright? That's all that negative and positive signs mean. But it's important when we do the math, because if you did this the first time and you didn't get 15 centimeters or 35 centimeters, you got, I think it's 60 or 84 centimeters, is because you didn't put the negative on the 60. And you went 1 divided by 60 minus 1 over 20, instead of 1 over negative 60 minus 1 over 20, which would actually give you a larger value. Okay? So the total distance between the two images would be 35 centimeters. Okay? All right, third question. Third question says, a 3 centimeter tall object is placed 6 centimeters in front of a mirror. The upright image that is produced is 1 centimeter tall. Identify the type of mirror used. Right? It is a it is a 3 centimeter tall object placed 6 centimeters in front of a mirror, and the image is upright. It's a positive value. Upright, upright, upright. Inverted, inverted. If it's upright, it needs to be positive, and anything that's positive comes with a concave mirror. Okay, so DI, this therefore the mirror is concave. And then it asks us, determine the focal length of the mirror. So the height of the object is 3.0 centimeters. The distance of the object is 6.0 centimeters. And it's asking us for not 1 over F, but F, the focal length of the mirror. The height of the image is plus 1.0 centimeters. Okay. One over DI plus 1 over DO. Pretty straightforward. But except for that, we don't have DI. What we do have is HI over HO is equal to negative DI over negative DO. Solving for DI, we're going to get HI times negative DO. I just took this sign with the DO when I moved it, divided by HO. So HI, 1.0, multiplied by the negative of 6.0, divided by height of the object, which is 3 centimeters. So DI is equal to negative 2.0 centimeters. Now I can figure out my F. F needs to be positive because it's F needs to be positive because it's a concave mirror. Well, I guess we shouldn't say that. We should figure it out. It can be a concave mirror and be negative if the image is between the focal length and the mirror, except for that I don't believe that it would be an upright image. Let's do the math. Let's see what the math says. 1 over negative 2.0 plus 1 over 6.0. We're going to get a value of 0.33 centimeters to the negative 1. That's 1 over f, so f is going to be equal to 1 over 0.33 to give us 3 centimeters. And we see that the value comes out positive, which is concurrent with a concave mirror. Okay, let's look at question number 4. Question number 4 says, a 5 centimeter tall object is placed 4 centimeters in front of a mirror. If the distance of the virtual image from the mirror is 2.4 centimeters, what is the focal length and type of mirror used? So it's a 5 centimeter tall object placed tall, not distance, placed 4 centimeters in front of a mirror. If the distance of the virtual image is virtual, di has to be negative. Equals negative 2.4 centimeters. What is the focal length? And what is the type of mirror? Okay. Focal length is 1 over f is equal to 1 over di plus 1 over do. So let's figure it out. There we go. Flip my paper. Okay, we're going to get making sure that we remember this negative from our listing. But we're looking for f. Remember, this is inverted centimeters. So 1 over negative 0.167 is going to be equal to 6 centimeters. And this value here is negative. So let's look at this. Focal length. A focal length that is negative can be convex, or it can be concave when the object is placed between the focal length and the mirror. The distance of the object is inside of the focal length. So it could also be a concave mirror. That is the answer. Okay. Now, question number 5. It's going to take us way back to grade 11 math, where we're working with multiple different kinds of denominators. Question number 5 says, a convex mirror has a radius of a curvature of 12 centimeters, which means C, right? C is R. If the image is 1/4 the size of the object, how far is the object from the mirror? Alrighty, let's look at this. This is the formula here. One over DO. Well, when we look at first glance, we can figure out F because F is equal to C divided by 2, which would be 12 divided by 2 is equal to 6.0 centimeters. When we go back to our sign convention chart, it says in the question, a convex mirror. All convex mirrors have a negative focal length, right? Perfect. So I have F. I'm looking for this. I need DI. How do I get DI? M is equal to negative DI over DO. I have M. I have neither DI or DO. Kind of at an impasse, you might think, but not really. This is what we're going to do. We're going to do a substitution. We're going to do a substitution equation. What we're going to do, because we're looking for DO, we're going to set DI to solve for DI. DI is equal to MDO, negative. Let's take this negative sign with it. Where we see DI in the equation, we can put negative MDO. So 1 over F is equal to 1 over MDO, negative, don't forget the negative, plus 1 over DO. Now I have these two pieces. I have focal length, I have magnification, and this is what I'm looking for. Only right now, we can't isolate DO because we have it in two different parts of two different fractions. What's the thing you have to make common? You have to make the denominator common. In order for this denominator to be common, we need to multiply 1 over F by negative MDO. We need to multiply negative MDO by F. And we need to multiply 1 over DO by M and F. Oops. What you do to the bottom, you have to do to the top. Now we can just add them straight across the board because the denominators are all the same. If I had 1/4 is equal to 2/4 minus 1/4, I would just be able to do 2 minus 1 and get the 1/4. So we needed it all to be the same so that we can isolate MDO. So we can say here, because these are all the same, we can go negative MDO is equal to this negative here. Don't forget there's a negative here. So negative f plus fm. Okay, so this is the negative from the negative MDO. This is the negative from this entire fraction, and this fraction doesn't have any. Then when we want to isolate for DO, we can go negative F plus FM divided by hang on, Harvey's. I added a negative in here. I didn't need to. I needed to just multiply this by MDO. I didn't have to multiply it by the negative M. I'm going to take this negative out. Because the negative belongs to this entire fraction, but we just need the MDO to come over. There, that makes more sense. So we have negative F plus FM divided by, not MDO. Jeez. Make a very complicated thing much harder when I don't pay attention to what I'm doing. I just had to divide this by M. Okay? It makes sense if you go really slow through it. I'm trying to rush through it. Okay, let's add in the information. DO is equal to negative 6.0 plus negative 6.0 times 0.25. All divided by 0.25. So DO, I'm going to have positive 6 plus a quarter of 6, a negative, which is still going to give me a positive value, divided by a quarter, and I should get a value of 18 centimeters. This is a diploma level question. This is, do you understand how the formulas interrelate? Okay? All right. Hopefully you had success.